Hello everyone, and welcome to our continuing lectures on basic data science modules. We introduced NumPy in some detail, and now that we have built up our ability to really work well with numerical data, doing various mathematical computations quickly and efficiently, let's discuss how we can visualize it. And throughout this lecture video, we'll continue to rely on NumPy as not only a source of fake data via its random submodule, but also for producing kind of analyses of that data. So throughout this module, this notebook, we don't use real data, but soon we'll move on to using real data. The only reason we're not using real data yet is because I don't want to spend time showing how to load data into a NumPy array, which is not something we will frequently do since we'll usually be working with pandas. And I would rather save that discussion for when we are actually working with pandas, since pandas has very nice tools for reading in various data files. Nonetheless, as described in the previous lecture, it's very useful to understand how pandas works by first understanding how NumPy works. So let's move on to the plotting. Matplotlib is the most popular and maybe oldest or most foundational Python plotting library. Much like NumPy is at the heart of many data science modules, Matplotlib is at the heart of several Python modules for plotting data or making data visualizations. While there are other plotting libraries that are more powerful or have a more expressive syntax, Matplotlib is still one of the most popular choices for quickly generating different types of graphs like bar charts, scatter plots, line graphs, etc. So I've defined a function here that will produce some, what I would call, quote-unquote, realistic stock prices. I'm not going to talk through every function of how, describing how this data is generated, but it might be instructive to talk through one of them. This stock price function we see takes two arguments: a number of days, so how many days do we want data for, and an initial price. The stock price has two components: some trend, an overall trend, and noise, random fluctuations. The trend is either positive or negative, so I make a random choice as to whether it's positive or negative. I choose a random number between 0 and 1 for the rate of growth. I limit the overall growth to 10% over the course of a year. So at most, this stock could rise or fall by about 10% over the course of a year, 365 days. And what I do is I simply multiply out that trend, that kind of coefficient, against all of the days, the number of days. So each day, this initial price, first of all, we start at the initial price, so 1 times the initial price, and each day we gain whatever fraction of this rise or loss is. This would maybe be a little bit more clear if I put it here. The plus 1 over there. So we start with the initial price plus some fraction of the initial price, 10% or less, positive or negative. Each day out of that progresses out of 365. And then the noise term is going to be 2% of whatever the size of the trend is. Some number between every day I pull out a randomly sampled number from the standard normal distribution, so somewhere between negative infinity and infinity, but most likely between about minus to plus 2, and mostly around minus 1 to plus 1. You've all seen this distribution before. It's the famous bell curve. So this blue curve here, the standard normal, most of the probability lies, it's the red curve. Most of the probability lies between minus 2 and positive 2. So that's how these stock prices are generated. I have 3 initial prices, 80, 70, and 65. And then I'm going, for each price in those initial set of initial prices, I'm going to make a line plot, starting from minus days up to today, 0. Today is day 0, and we count backwards the number of days. On the x-axis, we have our days, minus 365 to 0. And then on the y-axis, we have our stock prices. Let's just split this up for a moment. So this x component gives me the days, minus 365 up to 0. And then we also have an equally long sequence of prices, 1 for each day. So we have 2 arrays, one with the x values, one with the y values for our plot. We additionally give our plot a title, an x label, and a y label, and a legend to distinguish our 3 companies, starting with our 3 different initial prices. And we can see the trace of the price for each company. Company A and C don't really have much of an overall trend. Company B's price is steadily falling over the course of the year. And each company is subject to some random fluctuations from day to day. To generate this plot, I imported Matplotlib.pyplot as PLT. Often when we are plotting using Matplotlib, we will be using this pyplot machine, and usually that is aliased as PLT. And this is perhaps the most common way to make plots in Matplotlib. It's very quick. It's a little bit dirty in some sense. I'll describe what I mean by that later on. But we can just take this PLT pyplot machine object and use it to churn out the visual elements of a plot. So by repeating this plt.plot, we generate these lines. We create these different time series lines in our graphic. We can generate a title and our labels and legends, and we just chain together all of these various visual elements. And as long as they're all in the same cell of our Jupyter notebook, all of these plot dot somethings, they will get combined into the same figure. So this output is called a figure. It has the title, the labels, the different line plots. That's all part of one figure. And as long as we are working within a single cell and don't make multiple figures, for instance by saying plot.figure again, here we make two figures. I don't know why it output 3 here. 2 of them are the same. Oh, okay, I see. This was the second one. So this object was returned by the cell. And then this is almost like printing. It's getting pushed to standard out. So if the figures actually contained any visual elements, we would see those 2 different visuals here and here. Why don't we go ahead and make some visual elements? I'll just steal this line for the plotting. So we could have multiple figures with different plots. But as long as we don't explicitly create multiple figures, this plot state machine, I'll explain what I mean by that in a moment, but this PLT object will continue adding visual elements to the most recent figure. If we go to a new cell, it will automatically create a new figure. So PLT always gives us a handle onto the current or most recent figure created in that cell. So after this line, this PLT is hooked into this figure. After this line, this PLT no longer hooks into this figure. Instead, it hooks into this figure. And this is why it's called a state machine. Where our visual elements that we're generating using the PLT object go depends on the state of PLT. It depends on the history of the commands that we executed with PLT. So as we create new figures, the focus of that object shifts to the most recent figure. So this is why it's a little dirty, creating figures this way, is because it's stateful, and it's not necessarily clear from the code itself exactly what's going to happen. We need information about the state of the PLT object in order to be certain exactly what will happen when we do plt.plot or plt.title. A somewhat cleaner way of creating graphics is to use the object-oriented approach. So here, this cell illustrates that object-oriented approach. Here we're going to generate some data describing the shoe and jersey sizes of a football team. So we supply the number of players we want, the mean shoe size and the mean jersey size, and then we generate some random normally distributed shoe sizes, and we calculate the jersey size from those shoe sizes. It's just a rescaled version of the shoe sizes plus a little bit of random noise. Once we have our shoe and jersey data, we're going to create several different plots. We're going to create a histogram of the shoe sizes and the jersey sizes. We're going to additionally create a scatter plot of the shoe sizes versus the jersey sizes. And we're going to plot a linear regression line, a line of best fit, through that scatter plot. In contrast with how we made our plots of stock prices by simply doing plt dot whatever visual element we want to create over and over again, here we're creating objects that are permanent handles to different visual elements of our plot. So we create a figure using PLT, the plotting object, and we store that figure in a variable. And then anytime we need to work with this figure in particular, we don't do it through PLT, we do it through this figure object. So we can add a super title to the figure. We can also then create subplots and store those in these various axis variables. So we have axis 1, axis 2, axis 3. And we don't need to worry if we've most recently created visual elements in a particular subplot or a different subplot. And this gives us a lot of flexibility as to how we organize our code. So here we do all of our plotting for the first subplot, then all of our plotting for the second subplot, then all of our plotting for the third subplot, but we don't necessarily need to do it in that order. I'll show you what I mean in a moment. First, let's just see what this does. So here we have one figure with a title that hovers over all of them. That's the super title I made. We have two histograms. I'm going to add just a small line down here at the end. There we go. That's a little, well, that's almost better. What if I just do title here? Does that work? No. Okay, I'll get rid of this then. So we have two subplots for our histograms. The frequency with which each shoe size occurs, and the distribution of chest sizes for the jerseys. And then on the right we have another subplot with our scatter plot of shoe size versus chest size, and our line of best fit. And this is all a single figure. We could save this to a file, and all of these plots would appear together. Or we could, and then we could put that in a slide deck, or wherever else we might want to use this combination of plots. Now, I mentioned we could reorganize our code in a different way. So here we did all of our visual elements for the histogram 1 and then histogram 2, and then all of our visual elements for the line plot. But maybe what we want to do instead is first create all the visual elements, then plot the data. So we'll make our histograms and our scatter plot. We'll perform our linear regression and plot the line of best fit as well. And then maybe we want to do all the labeling. So this is a different way of organizing the code. And this is a very different logical presentation from what we had before. Before it would have been like, make subplot 1, make subplot 2, make subplot 3. And that's fine, and so is this. There are two different approaches. One is not better than the other. They just reflect different mentalities of approaching the creation of the plots. If it's easier for you to think about, okay, I'm going to work first on this subplot, then I'm going to work on this subplot, you can take the first approach we showed. If it's easier for you to think of, I'm going to plot all the data and get that to look just how I want, then I'm going to make all the labels and get those to look just how I want, or I'm going to do all the layout and get the layout right before moving on, then this approach might work better for you. But this is only possible. This approach is only possible because we took this object-oriented approach where we created variables to store our various visual objects so that we could refer to them later by name. This would not have been possible using the state machine approach of just using PLT over and over again, because once we had created these subplots, there would be no way to switch between them in the code and address one subplot versus another one. We would be stuck with whatever subplot we had created most recently. So the state machine is great. The PLT state machine is great for making very quick visualizations, but for more complex layouts like this one, it's very helpful to use this kind of object-oriented approach. We have another example here, again showing the state machine approach. Just another example. This doesn't really add anything to the plotting. Mostly this is just another example of like generating some realistic random data. I'm not going to spend more time elaborating on this example. What I do want to highlight is creating visuals is often a very specific and tailored. You're writing code that is very specific and tailored to a particular task and a particular data set. So compared to other instances in which we're writing code, where we're trying to solve particular problems, in those instances we'll recycle a lot of patterns, and there are certain patterns in how we might logically organize our approach to working on, say, some analytical problem. When we're creating plots, that's a little less true. And also, the code itself tends to be a little less coherent logically. And there's usually many ways to accomplish whatever we're trying to do. If you remember when we talked about the Zen of Python, one thing in there is there should be one, and preferably only one, obvious way to do it. We've already seen with plotting that there's two totally different approaches, both of which are valid and have different advantages and disadvantages. But in fact, there's usually many ways to create a visualization. Therefore, I suggest not investing a ton of time learning the ins and outs of any particular plotting library. Instead, what I would recommend is if you are trying to create a particular visual, sketch it out on paper and get a clear picture in your mind of what you'd like to make. And then Matplotlib or Seaborn or Bokeh or any number of data visualization libraries tend to have galleries of different visualizations people have made. And it might be, for instance, you want to make some violin plots. Maybe this is what you have in mind for your data visualization. So you can go to the gallery and find something that resembles what you would like to make. And the code is all there. Someone's written out code showing how you might make this in Matplotlib. And now you have a basis to work with that you can adapt to your own purposes. You can substitute in your own data. You can get rid of parts that you don't care about. For instance, maybe you don't care about all this color and all this stylization. Maybe you just want the thing on the left. Well, you can take just the part for the thing on the left. Here, you can throw away all the other stuff. Or maybe you want this part on the right, but you don't want the red coloring here. So you get rid of this part with the face coloring and the edge coloring. So a very quick way to get moving with visualization code is to go to the gallery of a data visualization library, find a visualization that looks like what you would like to make, and then take the code and adapt it to your own data and your own problem. That concludes our discussion of Matplotlib. In the next video, we're going to have a brief, high-level overview of pandas. If you've looked at the notebooks in the data wrangling directory, you see there is a pandas notebook. So we're going to go into much more depth. But in the next video, we'll simply introduce pandas and some of its functionality at a high level.